Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning to everyone. Greeting from London. Okay, today we're gonna continue our e-learning mode video recording lecture for Introduction to Queuing Theory Part 2. So today we're gonna start about the key variables in the queuing system or queuing theory. So what are the key variables? You can see here the lambda, mu. Lambda is a arrival rate. This is mu is a service rate, and these units on this part, the rate is the unit is 1 per second or s minus 1. Okay, this part, this part. So lambda and mu, the unit is s minus 1. And these parts, intel arrival time, waiting time, service times, are response times, all in second. Okay, all are in seconds. And this is number of jobs, or you can say people or traffic, is an item, whatever number in the system. So this one you don't have units. This one you don't have it. This is a rate, 1 over second, and this is the second, and this is the number of jobs, people, and traffic. So we're gonna learn about it one by one. Okay, the first one, tau, intel arrival time here. Tau is the intel arrival time between two successive arrivals, meaning that this, let's say this is traffic 1 here, and then this is traffic number 2, this is traffic number 3. So this is inter-arrival times. This is the tau. This is tau. And this is tau 1, this is tau 2, and so on. So this is inter-arrival times. Time between two successive arrival, like traffic, person, jobs, or whatever item you can think of. And the second one is lambda, mean arrival rate here. Mean arrival is 1 over tau. Basically 1 over tau. May be a function of the state of the system, like number of jobs already in the system and so on. S is a service time job. S is a service time per job. So if you go to the counter, let's say you want to renew your immigration, you come in and then your numbers appears, your turns appears. So you go to the counter. How long does it take in the counter to complete your job or your processing time? So this is S, service time per job. U, mean service rate per server, 1 over S. So this basically is 1 over S. And total service rate for M servers is M mu. So total server, okay, let's say the rate is 3 jobs per second, and you have M number of servers 3. So 3 times 3, 9, something like that. So total service rate for M servers is M mu. And N, you have number of jobs in the system. This is called a queue length. This N is a queue length. So this is a number waiting. This is a number waiting. This is the number waiting. And this is the number being served. Okay. So note, queue length also include jobs currently receiving service as well as those waiting in queue. So let's say this is the hospital counter, and this is the counter, and this is the people being served, let's say 3, and this is the people that still waiting. So this is a queue length. Q-U-E length. So this is a queue length. No, queue length includes jobs currently receiving service as well as those waiting in the queue. So you have NQ waiting in the queue plus being served. This you call a queue length. So NQ is the number of jobs waiting, NQ, NS number of jobs receiving service, and S. R is the response time for the system with time waiting, time receiving service. So R is basically W plus S. W waiting time between arrival and beginning of the service. W is the time arrival and beginning of the service. And S is the being served, the service time, which we have defined earlier in the previous slide, service time per job. And what is the rules for all queues? So the following apply to general GGM queues. This, remember the candle notation. Stability condition, arrival rate must be less than service rate, or L is less than mu. So finite population or finite buffer system are always stable. Instability, infinite queue. Of course, we assume in our system is infinite queue, but just don't get overworked on that terms. And another one is sufficient but not necessary is DD1. This is only for deterministic. Deterministic meaning that if the bus arrive 30 minutes per one bus, every 30 minutes one bus will arrive. So this is deterministic. You can determine bus number 1 arrive 30 minutes, bus number 2 after 30 minutes, bus number 3 30 minutes, is constant. So this is deterministic. Except for DD1, Q is stable, L lambda is equal to mu. Others, for stability, you must follow L is m times mu. Let's say you have let's say you have 20 people here arrive at the counter, but at one time they can only service like 10 people. Okay, 10 people waiting, maybe 5 people on the service time, and they have only two counter. So if like you arriving, some people cannot go in, or some people go in already and they give up, they just go out. So if this happens, okay, this part is a lambda, this part is a lambda, this part is the m, and this part is the mu, service rate. So if lambda is more than the m times mu, this system will be unstable. People will die waiting, or people just give up, or in hospital people just get sick and die. So it is important, the stability condition must be L less than m times mu. And then number in system versus number waiting. So you have number of system is the number waiting plus number being served. So this is the waiting. No, you're waiting at the counter, and this is counter 1, counter 2, counter 3. So this is the people being served. So this is an NQ, and this is NS, and total is N. This is NQ and NS. Sorry. So it's supposed to be subscript. So this is the NQ, and this is the NS. And number versus time. If jobs are not lost due to insufficient buffers, mean number of jobs in the system, or N, is equal to arrival rate time response time. So this is a very important formula. This is a Little's law. Okay, response time. Similarly, mean number of jobs in the queue. Let's say you want to find NQ. Okay, remember NQ and NS. NQ and NS, waiting, and this is N. So NQ is lambda times, okay, we have waiting time and we have service time. So number of jobs in the queue, arrival to mean waiting time, so LW, or NS is equal to lambda S. Okay, NQ and NS. This is known as Little's law. Number 3 and 4 is widely or popularly known as a Little's law. Very important law, very important mathematical equation for queuing system. And of course, you have time in system versus time in queue. R is W plus S. N is equal to NQ plus NS. I'm not sure. It's easier if you put NW plus NS, but the books say like that, so just follow the books, but it doesn't matter as long you understand how does this equation being generated. And R, W and S are random variables. So at random variables, meaning that we are in the stochastic process, stochastics or exponential or discrete. So all this must be a random variables. And another one's not that important, but just for you to understand, if the service rate is independent of number of jobs in the queue, service rate lambda, so it doesn't matter what's the service rate, this one, the number of jobs being served, doesn't matter how many arrive, it will just continue to serve without looking at lambda rate. So you have a coefficient of variation W and S. W waiting time, S is a service time, is equal to 0. And variance R equals to variant W plus variant S. Remember, this one is a waiting time and this is a service time. So in total, you got a response times. W plus S is the response times. So this is the service rate is independent of number of jobs in the queue. So what we go to the Little's law. It is a very important and very vital to the queuing system. And from this law, it can be, it can generate others, other equation as well. But the basic is Little's law. Okay, let's go on definition of Little's law. Little's law said that the mean number in the system is equal to the arrival rate times mean response times. So meaning that mean number in the system, number of jobs, number of traffic, number of persons, whatever items you can think of, is the arrival rate time means response times. Certain books may have a different notation for R or N, but for this course I just N is equal to lambda R, but you are free to change whatever symbols that you want, whatever notation that you like. Okay, this relationship applies to all system or parts of system in which the number of jobs entering the system is equal to those completing a service. So let's say this is a black box, this is a bank. Let's say 5 people come in, it must 5 people go out. If 5 people come in, only 3 people go out, meaning that you cannot really use a Little's law. Alright. Named after Mr. Little, 1961. It is more than 50 years already. Almost 50 years. Based on a black box view of the system. So if you are here, if you are somewhere outside, you don't have to go into that black box to know how many jobs left. If you know the arrival rate and you know the response times. Okay. In system in which some jobs are lost due to finite buffers, the law can be applied to the power system consisting of the waiting and serving position. So remember, this one is a waiting and this one is the serving positions. So some jobs are lost to finite buffers. The law can be applied to power system consists of waiting and serving position. So you can only consider here if some jobs are lost due to the finite buffers. Okay, this is the way you're proving a Little's law. Okay, let's say you have 3 packets. Packet 1 arrive at time 0 and departure time at time 4. Packet number 2 arrive at time 3, departure at time 6, and packet number 3 arrive at number 5 and departure at number 7. Okay, let's say we want to represent this, we want to visualize this in graph. So we have 3 ways how to make it. So number 1 is number of packets. Packet numbers. Packet numbers have a different meanings with the number of packets. Packet numbers 1, 2, and 3, and its arrival time. Okay. So at time 1, at time 0, packet number 1 appear. And at time 3, packet number 2 appear. Packet number 2 appear. But at time 1, it will, for time 1, it will, the departure time is at number 4. So you have here one big square. So arrive at time 0, departure at time 4. So this is done. So for packet number 2, arrival time is at 3. Arrival time is at 3 and the departure time is at 6. So 3, departure time 6. So okay, my one whole block here, you just shade it. And packet number 3, the arrival time is 5 and departure time is 7. So arrive at 5, departure at 7. So if you try to calculate the area of the shaded box, so you have here, this one is 1 2 3 4, 4 times 1 4, the area is 4 plus this one is, remember the area of rectangle, okay, area of rectangle is height times length or something, only 2, okay. So 4 plus this one is 1 2 and 3, 4 plus 3, and this one is 1 and 2 plus 2, so the area is 9 unit square. Okay, area you always mean with the units square. So number 2, ways number 2 is number of packets in system. Okay, at time 1, arrival time 0. At number 2, packet number 2 arrive at times 3. So in the system, instead of 1 packet at times 3, we have 2 packets. And then at departure time 4, the 1 packet will be leaving the system. So you back to square 1, only 1 packets. But at time 5, you have another packet left, so you have 2 number of packets. But after time 6, number of packets only 1, because one of the packet get done, already have a job done at time 6. So you only left with 1 packet, and at time 7, no more packets in the system because already being served. So if you calculate this one, the shaded area, the first one is 7 plus this is a 1 unit square, plus this is a 1 to 2 1 unit square, so you have 9 unit square. And similar with time in system and packet. So time in system, okay, the packet number 1 takes about 4 seconds. So you have 4 seconds, packet number 1. Packet number 2 takes about 3 seconds, and packet number 3 about 2 seconds. So that's how you represent the proving a Little's law using a graph. Okay, we also have a couple of ways to validate the Little's law without using the graph. The first one, you have to know the definitions. J is the area from previous slides. N is the number of jobs, n or equal to n small letter. T is the total time, or tau t, or summation of tau. And total time is also like R or T. L, lambda is the average arrival rate, N over T. W is the average time job in the system, J over N. And L is the average number of jobs in the system, J over T. Proof method 1 definition. So you have shaded area is equal to TL. T is total times average number of jobs in the system, or equal to NW. So if you take only this one, you bring this N over T times W. So here you have L is equal to lambda times W. Substitution, and you have lambda is L is equal to lambda W. So lambda from the definition is N over T times W. N over T over W is J over N, so you cancel down N here. So J over T is equal to J over T. So this is the tautology. So applications of Little's law. What is it? The application of Little's law. First, you can apply to just waiting facility of a service center, bank, ticket bus counter, what else? But nowadays you only do online. You rarely go to physical places unless you have to. And then mean number in the queue, arrival rate times mean waiting time. So this is n, how many number in the queue. Similar for those currently receiving the service, we have mean number in service, arrival rate time, mean service times. So in this one, you have s time, and how the number is ns. So mean number in service, arrival rate mean times, mean service time. So example, a monitor on the disk server showed that average time to to satisfy an input output request was 100 milliseconds. The input output rate was about 100 requests per second. What was the mean number of requests at this server? So you have here the average time to satisfy an input request of 100 millisecond. Average time. So average time, response time is 100 millisecond, or it is equal to 0.1 second. 0.1 second. And then you have the input output rate was about 100,000. So you have lambda here is 100 requests per second. What was the mean number of requests at the link server, at the disk server? So number of, we want to find the mean number, n is equal to lambda times r. So lambda you have 100 times 0. Request is 0. 100 millisecond is 0.01. Oh, sorry, R we already calculate 0.1. So you have here 10 requests. So arrival rate times the response time, 100 requests times 0.1 second is equal to 10 requests. So stochastic process is a function of time. Can be random variables which are functions of time. Stochastic process. So example 1 is NT, number of jobs at the CPU. Observe NT as several identical system. The number NT is a random variables. It depends on what program you run on jobs of CPU. And find the probability distribution function for NT at each T. Example 2 is the WT, waiting time in a queue. So this is all you have to concentrate. And this you represent the stochastic process very random. This is function 1, this is function 2, and function 3 is all very random. So this is stochastic process. What is the type of stochastic process? It's a discrete or continuous state process, Markov process, birth-death process, and Poisson processes. So first you have a discrete, finite, or countable. Let's say only let's say the packet only arrive at times 3 times. At times 3, and then it goes for n plus 1. So this is times 3, 1, 2, 3. But at times 4, or at times 3, another packet arrives. So this is discrete. There's no connection. This equal 3, and from 3 seconds it also has to go to somewhere else. So this is we consider a discrete. And continuous is a like time 3.1, 3.3, and then you continue. It's a continuous state process. NT is a discrete state process. The waiting time WT is a continuous state process. Waiting time is a continuous state process. N is a discrete. Okay, N, why is N discrete? Because N is a number of jobs, 1, 2, 3, number of traffics, and so on. So you cannot have a number of people like 1.1 people. No, it doesn't valid. 1.1 packet also it doesn't valid. So you have to use the N equal to, you have to use the N as a discrete state process. And the waiting time WT is a continuous state process. Because of times, you can set about 3.3 seconds, and then 3.7, from 3.7 become 4.8, 4.8, it become 51, and so on. So this is the why the waiting time is a continuous state process. Stochastic chain is a discrete state stochastic process. Not the time can also be discrete or continuous, discrete continuous time processing. So you have time can be also discrete, time can be also continuous time. So this is a continuous time. The district is like arrive at 1 a.m. 1 p.m. and this also arrive at 1 p.m. So you have and then after this is a bad example, sorry. So discrete continuous time process, time 3.1. So you just continue 3.1, 3.7, 4.8 and 5.1, so on. And Markov process, a very important process it is from Russian. Future states are independent of the past and depend only on the present. So what past is past. You don't bring the past inside the class. Something like that. And named after A.A. Markov, who defined and analyzed them in 1907. Markov changed the discrete state Markov process. Markov said that, what does Markov say? It is not necessary to history of the previous states of the process. Future depends upon the current states only. M/M/MQs can be modeled using Markov process. Okay, and the time spent by the job inside queue is a Markov process, and the number of jobs in the queue is a Markov chain. So like n number of jobs in the queue or just n number of jobs in the queue is a Markov chain, and Markov process total time spent inside queue is how long does it take to serve n. So this is the Markov process time span. So this is a Markov process, and this is a Markov change. So you have n number of servers and you have s. So Markov process is actually s. Markov change is a number of jobs in the queue, or like n, sort of. So this is a Markov process. What is the birth-death process? The discrete space Markov process in which the transitions are restricted to neighboring states. Process in state n can change only to state n plus 1 n minus 1. Let's say you have a traffic comes in and another traffic comes in. So the first one is L lambda, so the second one is lambda plus 1. Let's say this one of the packets go out is a death process. Packets come in is a birth process, packet come out is a death process. Example is like the number of jobs in a queue with a single server and individual array, not bulk arrivals. Okay, Poisson distribution. If the interval times are exponentially distributed, number of arrivals in any given interval are Poisson distributed. Let's say this traffic 1, traffic 2. This is a T1, T2, and so on. So this exponential random. Traffic 1, traffic 2, traffic 3 doesn't have a same, like it's difficult to process unless you average it. And this is a process we call a Poisson distribution. If the time system, the arrival rate and everything become like this, so use a Poisson process. The function is lambda times a to the power of lambda t. T is the time, and the probability of n arrivals in t is lambda t n times e times l over e, and you factor it by n factorial. So m is a memoryless arrival, Poisson arrival. So remember that I use a past example. Let's say there are 30 minutes one bus every 30 minutes. One bus every 30 minutes, and you have you arrive at times 28. So if memoryless, you still have to wait, because you still have to wait 30 minutes, and although you arrive at time 28. So this is a memoryless. So luckily our bus station, our bus system is a deterministic. So if they say 30 minutes, you arrive at 28, so you will have to wait 2 minutes to board the train. So example is like lambda is equal to 4 arrival rate. So you can like 4, if you want to find mu, you have to 1 over 4 or 0.25 jobs per second. Okay, Oh, so what is the Poisson processes? Interrival times S is equal to IID and exponential. Number of rivals n over a given interval t plus tx has a Poisson distributions. Number of rivals n over a given time interval t or t plus x has a Poisson distribution. Rival, Poisson process, or Poisson streams. Properties like you can merge all this. Lambda is equal to lambda I, summation of lambda I, lambda 1, lambda I, lambda k become lambda. I started with 1. Okay, 2 is splitting. If the product of job going to I substream is pi, each substream also Poisson with a mean rate of pi times L. So this is a splitting, this is a combining. Combining all the rival rate, this is splitting uh, all the substream. This one from L you go separate service rate. So if the arrivals to a single server with exponential service time are Poisson with mean rate L, the departures are also Poisson with same rate L, provided L is less than mu. So mu is the service jobs rate, and lambda is the inter-arrival time. So if it's a Poisson, lambda must be less than mu. Poisson process. If the arrivals to a service facility with M service sky centers are Poisson with the mean rate lambda, the departure also constitute a Poisson stream with the same rate L, provided L is less than I times mu I, I mean summation of mu I. Here the servers are assumed to have exponentially distributed service times. Okay, you have lambda is less than summation of ui. Ui, you have mu1, mu2, mu3, and so on. So for Poissons, you want to know better is like just remember the pasta property. Poisson arrival C times average. Okay, Poisson arrivals, random arrival from large number of independent sources. If an external observer samples a system at random instance, P, probability of system X, is equal to probability of state as seen by Poisson arrival is X. Example, okay, this is a deterministic example, D1, candle notation. Q arrivals is 1 job per second, service 2 jobs per second. So at time 0, packet number 1 arrives, and at 0.5 it leaves. 1.5 leaves. So the system see 1 packet arrive and 1 packet drop. Time number 1, it sees only 1 packet and then it's dropped, and so on. It's a deterministic. So all customers sees an empty system. So this this is a traffic. This is customer 1. Customer 1 arrived time 0, 0.5 it leaves. And then now come the customer number 2. It sees the empty system, but it's actually being served previously at time 0. So this packet number 2 arrive, see an empty system as 1.5 leave, and then you have number 2 see an empty system as well, only him, and so on. So what does the MD1Q arrivals of Poisson's process in the Poisson process that you want to make? So MD1 is a queue, arrival is 1 job per second, average service 2 jobs per second. Randomly sample the system. System is busy half of the time. So let's say time 0, you have 1 customer. And then between a couple of seconds, a couple of milliseconds, you have another one. So another one, this guy will see that okay, the system is not empty. You have 1 DJ. So one people, 1 customer. So at the moment now they have 2. At time 1, drop, done. The job have been done. Okay, at times 2, traffic number 3 is empty system, but when traffic number 3 and traffic number 4, static number 2 is okay. Static number 2 only sees empty system and it drops at time number 2. Okay, static number at time 2 point something, the first traffic arrives sees as empty system. The second traffic arrives, it sees they have a 1 customer, and together with they have 2 customers. At time 3 that drops, and 4 doesn't have any traffic. 5 you have another traffic arrive. So this is how poison process works. It's different from the deterministics, where it's a uniform and have a uniform sample rate. For poisons doesn't have a minimum. So traffic number one and traffic number two can be a couple of milliseconds different, and so on. So this is a relationship among stochastic process. The first one is the Poisson process, second one is the birth test, and third one is the Markov process. So the summary is candle notation, number in system, queue waiting service rate, arrival rate, response time, waiting time, service time, Little's law, process, Markov, birth, death, and Poisson. So that's it for today. It's a short lecture. I hope you understand, and if you don't understand, just inform me. We create forum or something. So thank you very much.